Hi folks, welcome back to 4.7 Optimization, and we're going to take a look at question number 5 in the practice packet. So this question says, you've been asked to design a 1-liter oil can shaped like a right circular cylinder. What dimensions will use the least amount of material? So let's go ahead and get started with a diagram. Okay, so my diagram is going to be of the oil can, and it is a right circular cylinder. So we've got the top, we've got the sides, and we've got the bottom. And we know that in a cylinder, some important dimensions are the radius of the bottom circle and the height of the cylinder. Now, it says that we are trying to find what dimensions will use the least amount of material. So the least amount of material. Now, when I think about what constitutes the material of a cylinder, what I'm thinking is surface area of the cylinder. So I'm going to go ahead and write the surface area formula for the cylinder over here. So the surface area of a cylinder is the two circles, all right? So there's a bottom circle and a top circle. And so I know the area of each circle is pi r squared. And then I know that there are two of them, so 2 pi r squared gives me part of the formula. Then I have to add the area around the can, sort of like where the label of the soup can is. And that part is actually a rectangle if you've ever peeled off the label of a soup can. And that part has an area of 2 pi r h. All right, so we have our surface area formula. Now it's longer than some of the other formulas we've seen, but when I look at this, I notice that there's too many variables. All right, we are still in single variable calculus, and so we can't have an R and an H on that side. We need to get rid of one of them. So let's think about our second equation so that we can get rid of one of these letters. Well, it looks like they give us some information about how big the can is, meaning that they want this can to hold 1 liter of oil. And when we think about a liter, we know that volume is going to be 1 liter. So volume is how much is inside of that cylinder. Now, we want to actually convert this to centimeters cubed because it's going to be easier when we find our radius and our height to have it measured in centimeters. So it turns out that 1 liter is equivalent to 1,000 cubic centimeters. And another formula that is helpful to know is the volume of the cylinder. Now, volume of the cylinder is pi r squared, because it's a circle, but then we stack them up to a certain height, so it's pi r squared h. Now what I can do here is set these two equal to each other, and I get 1,000 equals pi r squared h. And I think about which letter is going to be easier to solve for or isolate. And I notice that the h is going to be pretty easy to solve for. So what I'm going to do is I'm going to isolate this h, and then whatever I get for it, I'm going to go ahead and plug it in for that h. So if I isolate my h, I get 1,000 over pi r squared. So I just divide the pi r squared to the other side. And 1,000 over pi r squared is what I'm going to put in for my h. So this is going to go right in here. All right, so let's substitute that in and then see what we have for our equation. So surface area equals 2 pi r squared plus 2 pi r times 1,000 over pi r squared. So that's just substituting in the h with 1,000 over pi r squared. Now I'm going to try and simplify this before I take my derivative, because that's just a generally good strategy. We don't want to do more work than we have to, and simplifying is one way we can avoid that extra work. So to get surface area equals 2 pi r squared plus, let's see what happens. Well, this pi and this pi reduce to 1, so I don't have to write that. And then this r and one of those r's reduce, so I don't have to write that one. So what I get in my numerator is 2,000, so 2 times the 1,000, and then in the denominator I have an r left. Now because I'm going to be taking a derivative, I want to go ahead and rewrite this equation in a way that'll make it easier for me to see which rules I need. So that 2 pi r squared part stays the same, but the second part, maybe it's better if we write it as 2,000 r to the minus 1, because now I can see I'm going to need power rule for both the first term and the second term. So let's take our derivative. On the left-hand side, we will get dSA, or the derivative of the surface area with respect to r, equals, the derivative of the first term is going to be 4 pi r plus negative 2,000 r to the negative 2. Now, I'm going to do two things at the same time. I'm going to say I'm going to replace dSA dr with 0. The reason why I can do that is, again, I'm looking for the minimum surface area. So the slope at a minimum point is 0. Then I'm going to set that equal to 4 pi r, and then I'm going to rewrite this second term so that it'll be easier for me to solve. So minus 2,000 over r squared. All right. Now, as I get started solving this equation, what I'm going to do is a trick I've used before where I just get rid of fractions because it makes my life a little easier. And so the way I'm going to do that is I'm going to take the entire equation and I'm going to multiply it by r squared. So I'm going to distribute this r squared to the 0, to this term, and to this term. And what that gives me is 0 equals 4 pi r cubed minus 2,000. So that looks a little bit more manageable. I don't have to worry about any fractions here. And now I'm going to go ahead and isolate my r. So I'm going to add the 2,000 to both sides. I'm going to divide by 4 pi. And then I'm going to take the cube root. And this, if I type this into my calculator, will give me a radius of 5.419 centimeters. So what this means is that if I want to minimize the amount of material I use to make this oil can, the radius should be 5.419. Now, they want to know the dimensions, which means we also need to find the height of this cylinder. So what we're going to do is we're going to take this value that we found, and we're going to come all the way back to this equation right here. Everywhere we see an r, we're going to plug in 5.419, and then we will have the height of the can. So the height is going to be 1,000 over pi times 5.419 squared. And when you type that into the calculator, you should get 10.839 centimeters. So both the height and the radius need to be part of our answer in order to give the dimensions of this oil can. Now, if you want to think about this graphically, the equation that I would graph to check your answer is going to be this one. All right? And when you graph it, what you'll find is that it kind of looks like this, okay? And this point down here, that coordinate is going to be 5.419, comma, and whatever the surface area is, all right, which we didn't find, and that's okay. Whatever the surface area is, that would be the y coordinate. All right, so the radius is the x coordinate and the surface area is the y coordinate. All right, so folks, this is it for question number 5. We'll have one more example in this practice, so come on back and check out the video for practice question number 6. See you there.